Alright everybody, welcome to the next video. This one's covering section 4.3, proving triangles congruent by side, side, side. Talk about what that means coming up. But first thing I want you to do for this one is actually to do a little bit of an activity. And what I want you to do is I want you to find three objects of different lengths that could make a triangle. In other words, you can't have it where it won't make a triangle, but find three objects. You can pause the video if you want to after this explanation. What I want you to do is make a triangle with it. And I want you to make as many different triangles as you can. Just remember, with congruency, if you orient the triangle differently, it's still the same triangle. But how many different ones can you make? And that's what I want you to look for. So pause this if you need to. See what you can come up with. When you get back, we'll talk about what happens. All right. So, what you probably figured out is that there is only one triangle that you can make. With how the angles end up forming between the three sides, there's only one possible configuration that makes the triangle work. And that leads us to today's topic, because it's something that we can use to find out whether or not triangles are congruent. So, what we did in our last video was to prove that two triangles were congruent. We needed to show that all of the angles and all of the sides were congruent. But you don't need to do that. You can actually save yourself some time and find a few specific things that are congruent, and then you'll have your work done for you. It just takes less time in that way. One thing to consider is, if we only knew that the angles of a triangle were congruent, would that be enough information to say that the triangle was congruent? And the answer to that question, just think about it for a moment, we can discover by looking at an equilateral triangle. Move a little bit more into view. So here's our equilateral triangle. It's equilateral, also equiangular. All the angles are 60 degrees. They're all the same size. So that's going to be true for every equilateral triangle. So if I take this triangle, and let's say I increase its size like this, it's still equilateral. The angles are still 60 degrees. They didn't change. But is this triangle congruent to the one that we had before? The answer, of course, is no. It's not congruent. It's similar, but not congruent. They're not the same triangle. Their side lengths are not the same size, which makes them not congruent. So, we are not 100% sure the triangles will be congruent. In fact, it's kind of rare for that to happen. But, based on our activity that we just did, we do know that if our sides are the same length between two triangles, then they have to be congruent. That does tell us that they're congruent. So, the side-side-side congruence postulate says, if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. So, here we have a situation very similar to the one from yesterday's, but now it's in this new context of side, 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 and using it. Remember that if we want to name triangles, what we can do is sort of look for a pattern in how the triangle is formed. So let's say that I want this one to be in A, B, C order. Let's say I start at A and then go through B and finish up at C. Then we have triangle A, B, C. That's how we're naming it. Notice that we went through the 1 followed by the 3. If we want to do the same thing in the other triangle, what we're going to have to do is start at E, go up to D, and then go through C. So ABC ends up matching up with triangle EDC. And what we're going to start doing is we're going to have to start naming why we're saying the triangles are congruent. If we're using three sides to do it, like we're doing here, we know that all three sides are the same length, so we know they're congruent. Then we're going to say that we're doing it by side, 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 or SSS, which is short for side, side, side congruence postulate. It's way, way easier to write. So that's why we use it. So, determining the congruency statement and seeing if it's true, here's what we need to do for this. What we need to do is, so they're telling us that DFG is congruent to HJK. So if we look at DFG, starting at D, going to F, has us going through the one labeled with 2 lines, and then going through the one labeled with 3 lines. Let's look and see if HJK does the same thing. So if we start here at H, and then go up to J, we go through the 2-1 first, like we're supposed to, like we did over here, and then we finish up by going through the 3-1, which is what we're supposed to from over here. So then the answer is yes. Explaining our reasoning, well, basically, the points match up in both triangles. And that's how we know. Now look at this next example. We're told that ACB is congruent to CAD. So, if you look, this side clearly matches up between the 2 triangles because it's the same length. It's on this triangle, the bottom one, and on the top triangle at the same time, so it has to be the same length between the 2 of them. This side appears to match up between the 2 of them as well. They both have a length of 7. But we run into a problem when we look at the last side, because this one has a length of 3, and this one has a length of 4. That means that this cannot be true. AB and CD have different lengths. So we know that that one's not true. And then we have this last one over here. We're told that QPT is congruent to RST. So if we start at Q and go up to P, we go through the 2-1. Then down to T, we go down through the 3-1. Let's see if RST does the same thing. Start at R, go up through S, going through the 2-1, go down to T, going through the 3-1. Same pattern as the first one that we went through. So yes, this is actually going to read the exact same way as the first one that we did on this page. The points match up in both triangles. So there you have it. Side, side, side theorem. That's it. See you all in the next video.